Hey everybody, today we're talking about antiderivatives. Here we're in a situation where we know the derivative and we want to find the function that it came from. This actually comes up a lot. For example, we might know a velocity function and we want to know distance traveled. Velocity is the derivative of distance traveled. If we have a marginal cost function, we might want to find total cost. More generally, if we have a rate of change, we'd like to know the underlying function that's doing the changing. So here's the official definition. An antiderivative big F of x of a function little f of x is just a function such that the derivative of big F is little f. Basically, if big F prime is little f, then big F is an antiderivative of little f. This is most clear when we see a few examples. So we know if we differentiate 1/3 x to the third, we get x squared. So 1/3 x to the third is an antiderivative of x squared. Similarly, if we differentiate x squared minus 5x plus 6, we get 2x minus 5. So an antiderivative of 2x minus 5 is x squared minus 5x plus 6. A couple of trig examples. The derivative of sine of x is cosine of x, so an antiderivative of cosine of x is sine of x. And if we differentiate tangent of x, we get secant squared. So tangent of x is an antiderivative of secant squared of x. The moral of this story is that anytime we can do a derivative, we know an antiderivative as well. Antiderivatives are not unique, however. If we have a function, x squared, we can often make many antiderivatives. So all four of these functions here have the same derivative. All of their derivative, the derivative of every one of them is x squared. Notice that they differ only by a number being added on at the end, plus 1 minus 5 plus pi. When you differentiate any one of these functions, that number added on at the end will differentiate to 0. So that's why the derivative is always the same. So whenever we know an antiderivative, we know a lot more antiderivatives because we can just add any constant we like. So given one antiderivative, big F of x, we get all of the antiderivatives by doing big F of x plus c. We call that the most general antiderivative. The reason it's the most general antiderivative is the first line in this fact. Any two antiderivatives of a function little f of x can only differ by that plus c, by adding or subtracting some constant. There's no other way to get another antiderivative. So a lot of times you'll get asked, given some function, to find the most general antiderivative. Here's a table with some of the most common ones. These ones come up all the time. They're worth memorizing. The most general antiderivative of 0 is going to be a constant. If you differentiate a constant function, you get 0. The second line is particularly important. To get an antiderivative for x to a power, you've got to raise up the power by 1. Of course, when we differentiate, it goes down. So when we antidifferentiate, it goes up. That gives you the x to the n plus 1. Then when you differentiate x to the n plus 1, that power is going to come down. So we need a factor of 1 over n plus 1 to cancel it. Overall, we get 1 over n plus 1 times x to the n plus 1 plus c. This formula is valid for any exponent except -1. And the reason is clear. If you have n equals -1, on that right-hand side, you'd be dividing by 0. So you can't do that. We'll have to come back later and get an antiderivative of x to the -1. Similarly, the most general antiderivative of sine x is negative cosine x plus c, because if I differentiate negative cosine x plus c, I get sine of x. On down the line, we have antiderivatives corresponding to some functions that we know how to differentiate: sine, tangent, and secant. Obviously, there are many more antiderivatives. These are just some of the most basic. We can immediately start building new antiderivatives. So remember, when you're differentiating a sum, you can just differentiate the pieces, and that's true of antiderivatives as well. Similarly, if you have a constant times a function, you can just differentiate the function and multiply it by the constant. Same thing with anti-differentiation. Let's do one more example. So we have this function, little h of x equals x to the fifth minus 3x to the fourth minus 2 sine of x. And we'd like to get the most general antiderivative. We're going to do it piece by piece. First, we'll look at x to the fifth, then 3x to the fourth, then 2 sine of x. So x to the fifth, I'm going to raise up the power by 1 and then divide by that power. I get 1/6 x to the sixth. X to the fourth, I raise up the power and divide by the power, x to the fifth over 5. I multiply it by -3. So -3 times 1/5 x to the fifth, -3/5 x to the fifth. Finally, I'm going to do -2 sine of x by anti-differentiating sine of x to get negative cosine of x. Overall, -2 times negative cosine of x is positive 2 cosine of x. Finally, I add that constant at the end plus c to make sure I have the most general antiderivative. You can always check your work with an antiderivative by differentiating. Big H prime should be little h prime. So I run through big H, taking the derivative of each piece. I see that I get x to the fifth minus 3x to the fourth minus 2 sine of x. So I did the problem correctly.